Thank you very much, and I'm grateful to all of the organizers. Okay, so Andreas just gave us a lovely introduction to entanglement and measurement phase transitions, and I want to. Andreas talked about them from the point of view of effective statistical mechanics models that you can derive by averaging over random tensors or random unitaries. And I want to come at the same topic, but from a slightly different angle, which is tree tensor networks. Okay, so these will be large tensor networks with a tree structure where the individual tensors are random. So okay, I don't need to tell this audience, but tree tensor networks are more or less the simplest tensor networks that you can have beyond just one-dimensional tensor networks. And they have some nice properties, like you can efficiently contract them, and they've also been discussed as toy models for scale-invariant wave functions, like the simplest version of a mirror, something even simpler than a mirror. But what I care about here is that they also give us trees give us the simplest versions of entanglement transitions. In fact, maybe perhaps more or less the only examples of entanglement phase transitions which we have, which are exactly solvable, for finite bond dimension. So, today I'm basically talking about tree tensor networks as objects in their own right, but of course the underlying motivation is to try and understand more general entanglement phase transitions or measurement phase transitions in finite dimensional systems. And so the idea is that these simple trees can give us a window into a kind of mean field theory for those kind of phase transitions. And maybe I won't emphasize it so much in this talk, but there are also interesting connections to problems in classical statistical mechanics. Like, for example, an old problem which is a directed polymer that lives on a tree and experiences some disordered potential on that tree. There's a kind of toy model of glassy systems, disordered systems. Okay. So this talk, what I'll talk about is based mostly on a paper with Stidley Roy and Brian Skinner and Jonathan Ruman. And depending on time, I might mention some forthcoming work with Xiaozhou Feng and Brian Skinner, and with Braden Ware and Roman Besser. On the archive from maybe around 2020 or 21. Okay, so let me write a quick plan. So I'll first say a few words about the context to motivate studying the trees. So the trees may seem almost too simple. So I want to motivate them by just recalling some things about the finite dimensional problem, trying not to repeat too much of what Andreas has already said. And I'll describe one way in which we can arrive at the tree problem, starting with the more physical dynamics, quantum circuit dynamics, which will be a quantum circuit with all-to-all couplings, where you can apply a unitary between any pair of spins. That's closely related to trees. All right, then I'll describe the phase transition on the tree in its own right. And then, okay, if I have some more time, I'll talk about, so here I'll really talk about, and just talk about the distinction between random tensor networks and dynamics with measurements. So here I'll really talk about the random tensor network problem. And if I have time, I'll say something about putting back in the measurements in a particular simple model. Okay, so so I'm interested in the measurement transition in a quantum circuit or entanglement transition in a tensor network, which are really kind of structural phase transitions in tensor networks. So, for example, okay, which one could motivate in various ways, but for example, one motivation is that the entanglement structure of the tensor network is related to understanding the computational difficulty of various computational tasks. So, for example, in the case of with measurements, that could be how difficult it is to simulate the dynamics of certain kinds of open quantum systems or monitored quantum systems. Or it could be simply contracting some tensor network. So a cartoon of a tensor network in the disentangled phase, kind of extreme limit of that, would be one which sort of fell apart into disconnected pieces because, let's say, the bond dimension was 1, and then to contract the tensor network, all you have to do is multiply a bunch of local numbers. So for example, in the case of the measurement transition, the relevant tensor network, something which, we start with a unitary circuit. I'll draw it this way, some potentially random unitaries. And then we add these measurement events, so this is time. And formally, these measurement events are projection operators, so we can draw them like this. It involves some Rana-Ket projection onto some state on some of these bonds. So just to make the point that, which I'll mention later, use later, that formally these measurements are represented by projection operators, which you can think of as breaking a bond of the tensor network. So on that bond, bond dimension on that bond now takes a trivial value. All right, so this is the tensor network which describes the dynamics for a particular sequence of measurement outcomes. So if I feed in my initial state, and this tensor network will tell me how to, I can use this tensor network to construct the final state. And the kind of questions we could ask are, after evolving an initial state for a very long time, is the final state that comes out volume law entangled or area law entangled? Or we could ask, does the final state retain quantum information from the initial state? And these are all basically boil down to questions about the structure of this tensor network. In the random tensor network, we might have something which is structurally similar. So here we have some random tensors drawn from some probability distribution independently, each one an independent draw from this probability distribution. So for example, this might be a Gaussian random tensor. And we can ask the same kinds of questions. And the key difference between these two things is that in the case of measurements, there's Bond's rule, which affects how we sample these random tensor networks. So in the random tensor network, we just sample each node independently from some probability distribution we've chosen. In the measurement case, we have to sample the outcomes, so each of these projection operators is labeled by a measurement outcome, say maybe happen to be spin up this time. And we have to pick these measurement outcomes with the correct quantum mechanical probability, which itself depends on the state and therefore depends on the tensor network. So this means that the measurement outcomes are non-trivially correlated. And which you can think of as more or less, equivalently, you can think of this as built up from random tensors, but those random tensors have some correlations, spatiotemporal correlations between them. So, all right, so motivation here is that we want some kind of solvable version of these kinds of phase transitions. And so what kind of techniques do we have? So the first thing which Andreas already touched on is that you can consider a particularly simple limit where the bond dimension becomes very large. And in that limit, everything can be understood, well, at least let me imagine this version of the problem where I can think of these measurements as breaking bonds, and then everything can be reduced to the minimal cut formula for computing entanglement, or for bounding entanglement in a tensor network. And basically, the phase transition is reduced to classical percolation. So that means it just becomes a question of the geometry of the tensor network, which parts are connected to which, and so on. So that even that simple limit gives a surprisingly good picture of the two phases. There's an entangled phase and a disentangled phase. Even to the point of capturing some universal phenomena in those phases. But it doesn't faithfully capture the critical exponents at the critical point. So, as we already heard, the exponents at, say, one dimension 2. So 1 over d is like a RG relevant perturbation. So then one thing you can do to go beyond that is to derive these effective, what we could call in quotes, lattice magnets. So you get some effective spins, which are permutations. As in Andreas' language, members of the commutant. So in quotes, you basically you explicitly perform the disorder average for some observable you're interested in, and you end up with something which looks like a classical partition function. involving a sum over these degrees of freedom, which live at various positions in space and time, and have some effective energy. So this picture is very powerful, particularly in the entangled phase. So in the entangled phase, this gives a very nice picture in terms of domain walls in this sigma degree of freedom, which you can use to calculate all kinds of stuff. In fact, you can even extend that idea of these degrees of freedom to systems which don't have randomness. Just block A unitary dynamics or whatever. But what about the critical point? So the critical point is a much more challenging problem. So ideally, you'd like to coarse grain these degrees of freedom. To get some kind of, perhaps some kind of continuum field, let me just call it X, and some Lagrangian for this field, perhaps, and apply field theory tools. And that's, okay, this whole thing is very interesting in direction. We just had some very nice results obtained using that language. But it's quite subtle, and certainly we do not yet have exact results for, say, critical exponents in 1+1 dimensions. Or
question. So these new degrees of freedom living in this lattice magnet, are they defined along the time axis, or are still on the physical?
So the simplest way to think is that for every time you have a unitary, there's after you do this mapping, there's a spin associated with it. Yeah. Yeah. So this is an interesting direction, and we're also playing with these Lagrangians. But But if we want to get some actual exact, numerically exact results, it seems challenging. So today I want to talk about something else, which is to simplify the problem. Particularly to simplify the geometrical structure of the problem. So for example, we could take, instead of considering one-dimensional chain, we could take qubits without any spatial locality. So any qubit can undergo a unitary interaction with any other qubit. But it turns out that that problem is closely related to an even simpler geometry, which is the tree geometry. Yeah, so there's a way of starting with this quantum circuit dynamics and relating it to the tree, which I'll talk about in the moment. One could also just start with the tree. One could, for example, define a dynamical process which has a tree-like structure by bringing in activating more and more ancilla qubits at every time step. So maybe mention that at the end. Yes.
So that problem is it an equivalent of the area law phase, or because you?
I'll talk about how to define the two phases on the tree in a second. Oh, so you mean the old wall thing?
Yeah, exactly.
Right. So yeah, it's true that if we have all-to-all coupling, it doesn't seem to make sense to distinguish between volume law and area law anymore. So yeah, but it turns out it's not a problem. You just should use a different quantity to define the two phases. So one way to think about it is in terms of this, whether information is preserved from the initial time or not. So you can either have formally you can talk about it in terms of purification. Let's say you start with a maximally mixed state for these qubits, and then you run this dynamics. So if you're in the phase with a lot of measurements, then the measurements will rapidly transform the state into a pure state in order one time, basically. Whereas in the weak measurement phase, the system retains an extensive entropy for an exponentially long time in the system size. So this language of purification was developed by Gallens and Hughes. But you could also talk about this quantum state at a particular time, because although you may not be able to distinguish volume law or area law, you can still perhaps distinguish simple states from complex states in terms of how many unitaries you need to apply to produce that state or something like that. Okay, so what I'm going to say here is not really crucial for what I'll say next. I mean, I could just go straight to the tree and talk about how to study the problem on the tree. So this is just one way to get to the tree problem, or to motivate it by a perhaps more physical looking problem. I take this quantum circuit dynamics for n qubits, and I give them some discrete time dynamics. So the discrete time dynamics is just a sequence of operations. So each operation can be a unitary or a measurement. So I choose one or the other option with probability 1 minus p and p. Okay. So if I choose it to be a unitary, I apply a unitary to a random pair of spins. And if I happen to toss my biased coin and I find I should apply a measurement, then I measure a random spin. So, okay, so as I was just saying, the thing is there still exists a phase transition in that kind of dynamics with some critical PC. All right, and the simplification is that the space-time structure of this dynamics, which you could imagine as a kind of quantum circuit, is locally that of the tree. So it's a little bit difficult to draw the whole circuit because you have these non-local couplings. So let me just imagine that I follow the world line of one spin. Let's say spin number 1 at this time. Let me start off with some arbitrary time. And so here's a piece of the world line of spin 1. And I ask what's the next thing that happens to this spin. So maybe it undergoes an interaction represented by a unitary with some other spin, maybe spin 23. And then perhaps this spin 1 afterwards got measured, which means, as we see over there, that this world line ends in a graph. So this spin 23 that may then go on to interact with someone else. Spin 1004, and so on, and perhaps this one interacts with someone else, and so on. And the point is just, this one got measured. The point is just a very simple one, that when I consider this interaction, like the next thing that happens to spin 1004, who do they interact with? Well, they have of order n choices, and n is large, so it's very unlikely that this interaction is with spin 1 again. So the probability of forming some finite loop is of order 1 over n. So when n goes to infinity, there are no finite loops. So this is just a standard thing in many ensembles of random graphs, like Erdős-Renyi random graphs or something like that. A large graph, you don't produce any small loops. Local structure is a 3-tensor network. Well, we can even draw what this looks like. So we would start at some position. Let's say here. Well, actually, let me start with this unitary. No, okay, no, I'll start here. And you neglect what happens here. I follow this world line, and then there'll be a unitary. And I take this coordinate to be the distance from the seed which I chose. Root, or whatever. And then so okay, in doing this, I have to turn some unitaries upside down. Sorry. Okay. Let me not worry about the details, try to reproduce the details of this picture. Let me just draw schematically what we have. So we have here's a unitary. This is connected to some other unitaries. And we choose to arrange things not according to the physical time coordinate, but in terms of the number of edges which are required to connect you to the starting point. Right? I hope it's clear. So that would be something like if I take one of these, here I produce a tensor network which has this kind of structure. This one, let me. So I have no.
It's kind of a nice symmetric tree, or is it just you like this picture? I mean, tree just means it's a loop-free object, basically.
Just means it's loop-free, yes.
So you're not claiming anything more.
Not claiming.
Drawing this very nice tree-like trees currently. That's you're drawing these trees which actually look like the cliché trees.
Indicate that in this example, the number of descendants of a node can vary because basically, if something gets measured, then I lose one descendant. And this, so for example, this, if a node which has 3 descendants looks like a unitary with one of its legs turned around.
Kind of would like to fold all legs down, so you have the
I
seed at the top. Okay.
This is a generation number coordinate. All right, so this is one particular ensemble of random trees, which is defined in this way. You make the nodes from, let's say, high random unitaries, and then you delete descendants with some probability, which is related to the probability of doing a measurement.
That's not for cleaning, that's for drying. It's good he's a theoretical physicist.
Okay, beautifully all theoretical physicists here.
What's that?
Should be a tutorial.
Roger, it's a one-way causal connection. It's not forbidden.
So do I need to use this thing?
It helps. It will dry within like 30 seconds instead of 10 minutes.
All right. so, but now let me forget about that particular way of arriving at a tree and just talk about tree more generally. So tree, tensor networks, and random recursion relations. Okay, in particular, this would be random trees. So let me to simplify things. Let me imagine a tree which is a regular tree with branching number 2. It actually doesn't matter at all. It's trivial to generalize the approach to an arbitrary branching number. I'll assume the bond dimension is 2. Okay, so this is, all right, so let's say this, let me give this index here named alpha, and here beta 1, beta m, let's say. So I can think of this, well, one way I could think of it is as a rectangular matrix with a row index alpha and a column index, which is all of this. Some number of generations here, I'm going to call it k. All of these individual node tensors will be independently random. T alpha mu lambda.
Would you say what random means, or is it irrelevant?
Yeah, so we draw these T's from some distribution. And first thing is I'll assume this has a parameter in it. The distribution has a parameter. Which I can use to tune between the two phases. So, for example, okay, so I have some, let's say like that. So for example, one example could be that that here we have T being just a Gaussian random tensor, so a collection of each element is a complex Gaussian random number. And this here I could have T being a random disentangled tensor. So I could have T which is just made of 3 random vectors. And I can just linearly interpolate in a trivial way between these two things. I could take a T which is a superposition of this and that parameter R. Or another example could be more like that one. The parameter could be to do with breaking bonds. So I could have some probability R to just break this bond and therefore cut off this subtree. So then I'd have trees like that. With a random structure. So these details don't matter so much, but one thing which is important is that I will assume a kind of invariance of the probability distribution. We call the distribution P. And let me just write it very schematically, if it's not the correct formula, but the probability of some tensor T will be the same as the distribution will be invariant if I multiply some arbitrary SU2 unitary on a leg. Any SU2 unit. So, okay, it's sufficient to assume this for just the leg at the top, but for simplicity, let me assume it for all of the legs. So in that example over there with the random unitaries, then this property is present. Okay, so we'll see in a second that assuming this helps to simplify the treatment. Then, okay, so how do we define the transition? So we have a notion of an order parameter.
No? So the tensors themselves don't have to be symmetric. It's
No,
only
no,
the probability
yeah,
that
exactly.
has this property.
The order parameter, sorry, so going back to this thing. So of course we can think of it as a matrix, but another language we could use is to think of it as a state which has m plus 1 spins, I got m spins here. It's a convenient language. And by the way, the reason I include this bond sticking up here is because this is the the recursive unit which I can use to construct larger and larger trees. Yeah, okay. So if I think of it in this plus 1 spins, then the order parameter is basically the entanglement, the one at the top and the ones at the bottom. A and B. Like that. So this guy is A, and these are. So in the effective statistical mechanics language, this is going to basically be like what you would do for a classical stat-mech problem on the tree. Like if you studied Ising model on a tree, what you would do, you put a magnetic field at the bottom of the tree, and then I'd say, does this in the thermodynamic limit, does this magnetic field have an effect on the top of the tree? So this is, if I was to use this effective stat-mech language, this would be an analogous question. But I won't just work directly with a particular random tensor. Okay, so if we want to formalize this, so we have this tree T. So we can construct a reduced density matrix of A. Let me draw it like that. So I have to take T, which I now think of as a wave function, and I contract with contract the bar and the tet or whatever. Okay, divided by some normalization. Okay. So this is just a 2x2 reduced density matrix for this bond, this spin at the top. And then we could define the entanglement. Right? Or in fact, it's yeah. Okay. Let's say we talk about that. So then what we'll find is a phase diagram generically as we tune our parameter. SA, of course, it can't be more than log 2 since I just have one spin at the top. But I can have something like this with the critical vanishing at some RC. So over here we have a phase where the top and the bottom of the tree are effectively disconnected in the thermodynamic limit. And here we have one where, in some sense, information is communicated between the top and the bottom of the tree, even in the thermodynamic limit.
What is this telling you about the original problem?
Which original problem? The circuit? Yes, so okay. At the very least is presumably okay, so making that rigorously making a connection between the phase transition on the circuit, I don't know how to.
Well, even the meaning of this entropy in the original picture.
I think that maybe the simplest way to make the connection would be in this replica language.
What should I think of conceptually? I mean, it's what? It's a correlation of one point in the circuit with everything else in its past and its future, or?
I don't know. In some hand-waving sense, you take one bond in the circuit, and you can imagine that this bond is connected to two trees, one coming out of each direction.
Yeah, but that's the thing, though. The circuit's not about trees, really. That's what I would like to understand in the language of these random all-to-all circuits. Which is exactly not in the language of trees somehow, right? What does it mean in the original language?
So I don't think it's not so easy to interpret this directly in the language of the original circuit. The hand-waving picture would be that if the tree is in the disentangled phase, the large tree, that means that you take a bond in the circuit and you draw a big ball around it, and effectively somehow it doesn't matter if you break this bond because it's connected to these disentangling trees anyway. Okay, I can't give you a more precise answer.
But I guess it's consistent with the first example there, where for r equals 0, you have a random Gaussian, for r equals 1,
Yes.
disconnect. And then
Yeah. Let me just stick with the tree, and then in the tree everything is under control. I mean, this is just an explicit calculation for it. Okay, and then there's some critical scaling of this order parameter close to the transition, which turns out to be quite strange. Okay, and this critical point you can compute exactly for simple choices of tensor, like this case here where the tensors are made out of random integers. Alright, so
isn't this scaling like the costless stylus one?
I mean, it's functional form. It's something you have in costed stylus. Whether there's any underlying reason for that, I don't know. Okay, so let's make it a bit more concrete. So we have this reduced density matrix, which has eigenvalues like this. Let me choose to write it like that, where Z is between 0 and 1/2. And okay, it's convenient to think really use Z as the kind of order parameter which we work with. It's, okay. Z, there's obviously a trivial relationship between Z and the entanglement. And if Z is 0, then it's the disentanglement situation. Okay, so like with any problem on a tree, we just exploit the fact that you can construct the tree recursively. So you can build a tree with k+1 generations by putting together two trees with k generations. And one more of these node tensors. So these subtrees are two independent random instances. So if I write this in terms of the density matrix, okay, then okay, up to a normalization factor, it says that the density matrix, which is this contracted with the conjugate, is the density matrix of the larger tree, k+1. I take density matrices for two smaller trees, and contract them with T and T dagger. So formally I could write rho rho A k plus 1 is rho A k. So there's a prime because they're two independent instances of the smaller tree, and then T node tensor I think of as a rectangular matrix. Very well the same thing. All right, so the question is, how does the probability distribution of rho change as a function of k? And this is much simpler to think about because of this assumption we made. Because I only need to keep track of the eigenvalues, which because eigenvalues are normalized, I only need to keep track of this z. So z, I call it zk for real size k. So when I basically, because of this higher invariance, I can, unitary invariance, sorry, when I compute this recursive step to get a new density matrix, I can take the initial ones to be diagonal, and it has no effect on the probability distribution of the output. So rho k is 1 minus z, and rho k prime is 1 minus z prime, z prime. And I feed that into this, and I will get a zk plus 1 for the larger tree, which is going to be some function of the z's I've fed in and a random node tensor. And it's simple to just explicitly work out what this f is, and also to Taylor expand it when z is small. In other words, when you're close to the critical point or in the disentanglement. So if we do that, then simple exercise, you get zk plus 1 equals some constant, positive constant times zk, another positive constant times zk prime, and some higher order terms. And we'll need these constants explicitly, but you can write them, so it is some kind of determinant on the top, and something similar for A prime, but with the two legs of the tensor exchange. The key points are is A and A prime at random positive constants, which depend on the tensor. So the linear part of the recursion relation is the most important thing. Understanding the linear recursion relation is sufficient to find out where the transition happens. You need to put these nonlinear terms back in to to understand the entangled phase. And remember that Z is basically the entanglement. When Z is small, it's like the second Renyi entropy is 2Z or something. So these kind of linear recursion relations are very rich, so that's the problem. So if you drop these nonlinear terms, that's the problem which is related to the directed polymer on a tree. So the polymer on the tree has a recursive expression for the partition function, which has exactly the same structure. And it's related, surprisingly, to traveling waves, like the FKPP equation. So it's classic paper by Derrida and Spern.
Why are you interested with Z small? I thought you might want to expand above, solve for the critical point and expand above that.
The critical point is Z equals 0. Z equals 0 is all in the entangled phase, Z goes to 0 exponentially. In the disentangled phase, Z goes to 0 as the tree gets larger. All right, so the general theory of such linear recursion relations. So in this particular case, so there are two additional things. So one is that we have to worry about these nonlinear terms at some point, which is what will lead to an actual phase transition. And the other thing, which is that there's some nice properties, which is that this unitary invariance fixes some moments of these A's, independently of the details of how you chose the tensor, which means you can get kind of exact results fixing some quantities which in the general directed polymer problem would not be fixed. So,
question,
yes.
What information you get from the KEP equation? There's the wavefront and so on. How
Let me, I'll make it, right now I'll give you a very hand-waving picture of why it's related to traveling waves. So for now, let me simplify things by forgetting about this. So we want to characterize the probability distribution of zk as a function of k, particularly for large k. K is the size of the tree. So let me define something which, okay, maybe the notation is a bit confusing, but let me call it pk of x, capital X, which is just the probability. The logarithm of z is greater than or equal to x. It's basically the cumulative distribution, or 1 minus the cumulative distribution of logarithm of z. So we can imagine drawing this with x, p, x. So this is something like a 1 minus the cumulative distribution. So very negative x, it will be 1, and a large positive x, it will be 0. So there'll be some transition region, and this position, this transition region, is just the logarithm of the typical value of z. And this might be for a tree of k generations. And then in principle, if I know this probability distribution, I can iterate this transformation. So in principle, you could write, if you know the probability of z, k. So these are two independent these z and z prime are both drawn from pk. So then I can write a formula for what pk plus 1 is. And so there'll be some modified probability distribution for k plus 1. And you can imagine iterating that. So this is like the traveling wave which is moving. And this coordinate is like space. And the number of generations of the tree is like time. And what's very surprising, and what Derrida and Spern showed, is that this kind of process is closely related to partial differential equations for traveling waves, like dt phi equals dx squared phi plus phi 1 minus phi, which describes, front invading a region. But so the most basic thing underlying that analogy is just translation invariance. So, maybe I don't have to cut this. So the depth of the tree, k, is like time, and the this x coordinate, which is basically logarithm of z, becomes space. And you see that this, it makes sense because this equation is kind of translationally invariant in time and space. So I apply the same recursion at every k plus 1. And if I multiply all of the z's by a constant, the equation doesn't change, it's homogeneous. And that's like adding a constant to log z. So you can hope to find a solution which is like a traveling wave with some speed. And basically, what is important for what phase you are in is the sign of this v. So I have this probability distribution. And so in the disentangled phase, this traveling wave is moving to the left, which means that the logarithm of z is going to minus infinity. And z is going to 0, like e to the minus absolute value of v times k. But as you change the parameter in the probability distribution of the node tensor, then you can, this speed of this traveling wave may change, and then we may find that it's positive. Okay? So then that would tell us that z is going to infinity, which obviously can't happen because z is bounded, it's the eigenvalue of the density matrix. And so then what happens is that in this phase, because z is not getting smaller and smaller, you have to put back in the nonlinear terms in the recursion relation. And the nonlinear terms basically impose a wall, which this probability distribution is trying to push up against, but it can't go past. And there'll be some that competition between this v, which wants to be positive, and the nonlinear terms will set some typical value of z. Yes.
Is it possible to see like this propagating wave as some kind of entanglement front or correlation front in the picture where you consider your system as a m+1 spins?
Yeah.
So is there also like a concept of some kind of finite group velocity then here? Like
are you asking about relating this to this sort of geometrical structure of the tree itself?
Well, if you could see this wavefront as some kind of correlations propagated through your lattice, let's say, you can relate it to some kind of libero in some bound, some locality of finite speed.
What you can think of is that this is really, like, if you're in this disentangled phase, then these correlations between the top and the bottom are carried by some paths.
Yeah, exactly.
Between the top and the bottom. And Z is kind of summing up the contribution of all these paths. And basically, actually, what happens in these models with the unitary invariance property is that if you're in the disentangled phase, it's basically one dominant path. And this e to the plus or minus, e to the minus k is telling you like how much the correlations are attenuated as you go along this path. But you have to choose the optimal path.
It doesn't tell you about the existence of additional path on top of. So there's one path, but there might be some branching of those paths.
The branching paths are coming to do with the nonlinear terms.
Ah, I see. Yeah, of course.
So they're important in the entangled phase. All right, so I will skip the details of analyzing this traveling wave equation. So there's some technology for doing that, which basically involves you introduce kind of.
Also a proper sponge, by the way. It's probably working better. It's on the first table in front of David.
Oh, thank you. So to analyze this more carefully, you introduce a generating function, and then you write how the generating function transforms in the recursive step. And you make the traveling wave ansatz for the generating function, and then there's some logic which is the same as in the FKPP equation for working out. So you'll find that this, you can find a traveling wave solution for any velocity, and there's some logic which was developed for the Fisher KP equation for working out which is the physical velocity which the thing travels at. But, okay, so crucial. Yeah, everything boils down to, there was this A somewhere, which was the coefficient in the recursion relation which depends on the tensor, and everything just boils down to knowing moments of A. And then because of this unitary invariance property, you can show even without knowing the details of the node, just from knowing the unitary invariance, you have some identity which is like a to the 1/2 log A equals 0, and this basically enough to write a formula for the critical point. So that's something like this. RC. So in this example where we break bonds at random, say we break a fraction R of bonds, then you have RC is the critical fraction of broken bonds is 1 minus 1 over 3, and then the average of the square root of A. Okay, and if these things come from the random unitaries, then this has some value. You can get by doing some averages over the unitary group. Okay, and then the surprising thing is you can ask about the critical scaling here, and so that's surprising because trees you normally think it's something like mean field theory. It's similar to what happens in high dimensions. Like in the Ising model on a tree, it's similar to the Ising model in high dimensions. It's mean field scaling. So here there's a kind of mean field theory, but it's a strange kind of mean field theory with this exponential scaling, which I already wrote. Okay. So the lesson basically is that, there's some kind of solvable mean field theory of the entanglement transition, but it's sort of more interesting than you might have expected. So what we believe is that there's this kind of non-trivial structure of the critical point even in high dimensions. Okay, an open question is how to reconcile this kind of analysis, which is just working directly at the level of the probability distribution, with the replica or the effective stat mech treatment, which Andreas was talking about. How do you apply that to the tree? And understand this exponential scaling and so on. And there's interesting work in that direction by, Lopez Piqueras, okay, but it's still not understood how to reproduce this kind of behavior from the replica language.
Is that the old work for a year or two ago, or
Yes,
is it the one? Okay.
So they had some ansatz. It gives a different scale. Okay, so I think I've already gone over time. So there are various extensions. So in fact, you can, if you just look at these recursion relations, you can, by playing with the distributions of these A's, you can get something which is like a line of critical points with different universality classes for the phase transition. And we believe that also in the entanglement transition, you can have different universality classes on the tree. There's like you can think of this as kind of strong disorder. And there's some different behavior at weak disorder, which is more like conventional mean field theory. Okay, we have some work on that with Braden Ware and Romain Vasseur, which should be out soon. Okay, and there are many interesting connections with questions about how connections with field theory and stuff like that. Let's see. So I should stop. But if
No, you take 5 more minutes.
okay, okay, thank you.
Something. The way to start questions is up.
All right. So in that case, what I wanted to, I think, 5 minutes to talk about is I want to give this tree a dynamical interpretation, so I want the vertical coordinate to be time, and I want to ask about the difference between random tensors and measurements. So let's consider a very simple kind of dynamics, where I start with one spin, and then I somehow, at every time step, I introduce another ancilla, which this spin can interact with. So I get a number of active entangled spins is increasing. And okay, we can ask about exactly what happens at this node in a second. Okay, and we can ask exactly the same questions as before, like is quantum information about the state of the initial spin preserved in the final state, or has that information been revealed by measurements, and so on. So here we start with the state of one spin, and we try and scramble this state into many spins, but then at the same time we need to do measurements which try to extract this into. And we can also do some kind of inverse of that. I can start with many spins, and then in each time step I could, maybe they interact, but maybe I, in each node I measure one of the spins and throw it away. So one of them gets a measurement and then I throw it away. So the number of spins decreases, and again I can ask is there non-trivial mutual information between the initial state and the final state? So let me focus on this case, and to be more concrete I could imagine that, well, first thing you might try would be to say that this node is, I take two spins, I do a unitary, and then I measure one spin and discard it. But that's a bit too simple because that's an isometry and all of the information is preserved. So to have a non-trivial parameter, what we did is put weak measurements on these bonds. So again, these weak measurements will also have random outcomes. All right, so it's easy to see what happens if these weak measurements become projected measurements. Then each bond, just break the tree, and no information is preserved. And in this problem again, we'll have the same kind of phase diagram. We compute. Say we start off in a maximally mixed state, and we ask what is the one moment entropy of the state which you get at the end. And then there's a parameter theta which controls the strength of these weak measurements. And where this entropy dies, and so here the measurements are projecting the final spin into a definite state. So the key points are that, again, the measurement outcomes are random according to Born's rule, so this is like any q equals 1 in your language. And more importantly, so these node tensors T, they depend on these measurement outcomes, so they have some kind of correlations. But if you want to, you can also switch off the Born's rule randomness. So we could modify the problem and insist that all the measurement outcomes are +1. And so we could either study the true measurement problem, where the measurements are random, or we could study so-called forced measurements, where we do some post-selection and we only consider samples where the measurement outcomes are +1. And so then that problem becomes like the random tensor network with independently random objects. So you will get different curves for those two cases. This one is measurement. And this one is the force measurements, or the thing which is like a random tensor network. So for the force measurement, the recursive procedure is exactly like what I described. For the true measurements, it's slightly modified because the node tensor is correlated with the density matrices you're feeding in, but there's still a kind of recursive operation on the density matrix. So all right, but anyway, it turns out both those things can be solved analytically by the same kind of methods. And there are some differences. So there's a critical exponent, lambda, which is 1 in these models for the random tensor network, or the forced measurements, like a half, and 1 for the true measurements. So in both cases, you have this sort of exponential scaling. But at the critical point, you have a probability distribution for the entanglement. And this lambda is telling you how broad this probability distribution is. So if you consider the average value of z, then it's like the typical value, the power lambda. So in the case of the random tensor network, the distribution is much broader. And so the mean is much larger than the typical. Mean is dominated by rare events, is much larger than the typical. All right, so the last thing I wanted to say. So the trees give you some solvable examples of entanglement transitions, which is surprisingly rich. It's kind of mean field theory, but different to sort of standard mean field theory of Ising or whatever. It might be a way to be able to start to get some rigorous results, because the analysis of the tree is just kind of zero-dimensional analysis. You have a recursion relation on finite-dimensional matrices. Presumably some things can be made rigorous about that. And there are lots of scope for extensions. So there you have a Clifford tree. And I'm sure I've written something which I can't read. So, okay, yeah, and there's lots of interesting things about how to relate this to field theory. Thanks very much.